The next time you drive through a mountain tunnel or ride a subway deep underground, just stop and think for a second. You're in the middle of this incredible feat of engineering, and most of it is completely invisible. It's not just about digging a hole, it's about understanding the rock itself. And that's what we're talking about today, the hidden science of rock mass classification. It's the system engineers use to build these massive structures, and most importantly, to keep us all safe.
I mean, really think about it. What actually keeps a mountain from crushing a tunnel? It is the ultimate high-stakes question for an engineer. And the answer isn't just about pouring more concrete or adding more steel. The real secret, the real magic, is in understanding the rock's own strengths and weaknesses and predicting exactly how it's going to behave before you even start digging.
You see, the biggest enemy for any underground project is just one thing: uncertainty. Every single rock mass is a totally unique and complex puzzle of cracks, joints, water, and stress. So before you can build through it, you first have to figure out what you're up against. And that is exactly where classification comes in.
Now, this wasn't always a hard science. Not at all. For a long time, tunnel building was really more of an art, something based purely on gut feeling and experience. The journey toward a more scientific approach started way back in 1879, but it was Carl von Terzaghi in 1946 who first created a descriptive system based on how much load the rock would put on a tunnel. The real game changer, though, that came in the 1970s with systems like RMR and the qsystem, which finally turned messy geology into cold, hard numbers.
So let's go back to that key figure, Carl von Terzaghi. This guy was a real pioneer. He was one of the first people to stare into the geological chaos of a mountain and actually try to bring some order to it. He wasn't using complex formulas, not yet. He was using careful, expert descriptions to categorize the ground that engineers were facing.
And you gotta love his descriptions. They were so vivid. He didn't just say, oh, that's bad rock. No way. He described things like blocky and seamy rock, where you have fragments that are totally separated, or squeezing rock, which he described as slowly advancing into the tunnel after you've dug it, and even swelling rock, which actually expands because of clay minerals. For the very first time, these kinds of terms gave engineers a common language to work with.
But a shared language can only get you so far. The real breakthrough, the thing that changed everything, was figuring out how to turn those descriptions into actual data. Engineers desperately needed a way to objectively measure and score the rock, so they could compare different sites and design support systems with real mathematical confidence.
And the first big step in this direction was something called the Rock Quality Designation, or RQD for short. It was developed by Don Deere back in the 60s, and it's a simple but really clever way to get a number for rock quality right from a drill core. It's just the percentage of solid core pieces that are longer than 10 centimeters over the total length of the drill run.
And this picture shows you exactly how it works. It's brilliant. So, let's say this is your 200-centimeter drill core. The engineers literally ignore all the small broken bits and only measure the solid chunks that are over 10 centimeters long. So here, they'd add up 38 plus 17 plus 20 plus 35. Then they divide that total by the full length, 200. And that gives them an RQD of 55%. It's so simple, but so powerful.
But here's the thing. RQD is just one number. And a rock mass is way more complex than just how broken it is, right? What about the number of fractures? How rough are they? Is there water flowing through them? Modern systems take RQD and combine it with several other critical factors to build a much more complete picture.
Honestly, the best way to think about these modern systems is like a credit score, but for a rock mass. Just like a bank looks at your income, your debt, and your payment history to create a single credit score, well, engineers look at rock strength, fractures, and groundwater to generate a single quality rating for the rock.
And in the world of geotechnical engineering, there are basically two major credit reporting agencies. You've got the Rock Mass Rating, or RMR, which adds up ratings for 6 different parameters. And then there's the Tunneling Quality Index, or qsystem, which uses a multiplicative formula. They tackle the problem a little differently. For instance, RMR includes rock strength directly, while the qsystem puts more focus on the stress that's acting on the rock.
Okay, so this is the famous qsystem formula. Now, don't get intimidated here. The point isn't to memorize the math, but to appreciate the logic behind it. This equation is just an incredibly elegant way of organizing geological info. It groups all the parameters into 3 pairs that basically balance the rock's good qualities against its bad ones.
So what it really does is ask 3 pretty simple questions. First, what's the block size? It gets this by dividing RQD by the joint set number. Basically, how big are the chunks of rock? Second, how strong are the connections between those chunks? It calculates this by dividing the joint roughness by the joint alteration, which tells you how much friction there is. And third, what outside forces are acting on the rock. This is found by dividing the water pressure by the stress reduction factor. And boom, that gives you the active stress.
So great, we have our Q value, our rock's credit score. Now what do we actually do with it? Well, this is where the magic happens. This number gets translated directly into a real-world construction plan. That score tells engineers exactly what kind of support the tunnel is going to need to stay stable.
The process engineers follow is actually super logical. First, they go out to the site and they gather all the rock data they need for the formula. Second, they plug that data in and calculate the Q value. Third, they figure out something called the equivalent dimension, which takes the tunnel's size and its purpose into account. I mean, a temporary mine shaft doesn't need as much support as a permanent subway station, right? And finally, they take those two numbers to a chart to find the exact support they're going to need.
And this chart, this is the payoff. This is the heart of the whole Q system, where all that data finally comes together. Along the bottom, you've got the rock quality. That's our Q value. And along the side, you have the tunnel's size and importance. Where those two lines meet, well, that tells you exactly what to do. Whether it's just a few bolts, systematic bolting, or heavy-duty reinforced shotcrete.
Let's just trace a quick example to see how it works. Say our Q value comes out to 4.5. That's what we'd call fair rock. And our tunnel is 15 meters wide, which gives it an equivalent dimension of about 9.4. So we find 4.5 on the bottom, we go up until we meet the line for 9.4 on the side, and bam, we land right in reinforcement category 4. And the chart tells us precisely what that means. Systematic bolting, plus a layer of shotcrete between 4 and 10 centimeters thick. Absolutely no guesswork.
So you can see how these classification systems just fundamentally changed our ability to build underground. They gave us a rational, data-driven framework for making some of the most important and high-stakes decisions in all of civil engineering.
At the end of the day, that's what this is all about. Rock mass classification is the tool that lets us transform the messy, unpredictable chaos of geology into the clarity and confidence of a solid engineering plan. It's how we manage uncertainty so we can build safely, efficiently, and more ambitiously than ever before.
But, and this is a big but, even with these incredible tools, engineering is never just about plugging numbers into a formula. Experts strongly advise using at least two different systems, like RMR and Q, to cross-check the results. It's a powerful reminder that these systems are amazing guides, but human judgment and experience are still absolutely essential to guarantee safety.
Which, leaves us with a really fascinating question for the future. As we keep pushing the boundaries, building tunnels deeper, wider, and in more complex ground than ever before, how will we need to adapt our understanding of the Earth itself? And what new tools will we need to invent to continue building safely into the great unknown?